Hello everybody. In last video we have gone through the literature survey about this experimental investigation of oscillatory flow, pressure and pressure drop through complex geometries. So in this phase, I have taken the uh, we will discuss the numerical simulation part of this. So we will see the CAD model, numerical simulation, and the results of this phase. So for the CAD model, I have generated the CAD model given in the paper, which is a rectangular duct and rectangular duct with the different obstacles in the middle. So for first case, I have taken the rectangular duct itself without any obstructions and try to simulate the results. So this is the geometry with the obstruction, which is a simple rectangular block inside the rectangular duct. So this duct is of 300 mm width and a height of 17.3 mm. There is an ambiguity in the paper, but I have assumed that this has to be 17.3 mm for the simulation. So this was generated with the help of CATIA software. And for the numerical simulation, so as a first case, the rectangular duct with no insert is simulated. Regarding the piston's position, so one piston is set to be as a reference point, and another piston is adjusted accordingly. So for this, there is a 180-degree phase angle difference between the two pistons, which means the two pistons are moving in the same direction. So the frequency I have taken is 5 Hz, and these are the formulas used to calculate the maximum velocity, which has to be used for the preparation of the expression for inlet velocity. So X max is the uh, length, and V piston is the sweep volume of the piston, and AM is the minimum cross-sectional area, which can be calculated with this formula. These are all provided from in the paper itself. So W is the width of the rectangular channel, and H is the thickness of the insert, and B is the breadth of the rectangular section. So with these formulas, it is calculated that Umax is to be 2.36 meter per second for this particular frequency. So regarding the mesh, default ANSYS Fluent mesh is used, and element size is given as 3 mm, which is calculated from the CFL number. And since it is an oscillating flow, velocity cannot be given as a constant, and I have used the expression function for giving the oscillating flow. So this is the equation used. This is the maximum velocity, and this is the sine part. So which is 2 pi f into t. So this is multiplied with the pi and 2. So and this is the t. So for inlet 2, since it is a 180-degree out of phase, and a plus 180-degree, which is pi radians, is added. So regarding the results, I have extracted the graph from the paper with the help of Webplot digitizer tool, and this is the approximated graph from the original paper, and this is the simulated graph from the numerical simulation I have run. So you can see there is a difference in the values, but the trend is same. Even even in the paper, the authors have mentioned that this difference of in peak shouldn't be there. Ideally, it should be same because it is a sine wave. They are giving the input as sine wave. The difference in this peak is mainly due to the manufacturing defects of the motor and experimental setups. The defects in experimental setups. One of the defects mentioned in the paper is the belt wear and tear of the driving the motors could be out of sync and a perfect sine wave cannot be replicated. But the advantage we have in numerical methods is that it doesn't have any physical defects, so we get a pressure output of a perfect sine wave. So this is the result I got. So this is a video generated from the results, and it is simulated in TechPlot. So you can check it again. And as you can see, the pressure is varying in a sine wave manner. Thank you.